Hello everyone. In this video today, I'm going to be covering some of the new reactions that I previously did not think would be on this exam, but I'm just going to show which ones I'm referring to. So these are reactions I think if she hasn't already, she covered them on Thursday, and if not, she's going to cover them on Tuesday likely. So you'll see some of these, and this is page 7 of the reaction sheet. And so I'm just going to, I don't know if all these are going to be on the exam, but I'm just going to cover all of them. Um, and I might cover maybe the first one on this page. But you will not have this on your exam. I'm very sure of that. So page 7, okay? And I'm just going to explain these today in this video. So the very first reaction that I want to cover is the called dithiane synthesis, okay? And this is basically the conversion of a dithiane. Um, dithiane Dithiane is this molecule right here, okay? So this is the dithiane, and we're going to convert this into either a ketone and aldehyde. And the process of doing that is through the use of BULI, and the second step is this RX reaction, okay? And then the last step is H3O plus combined with HgCl2. And I'm gonna explain how all these steps work out. You don't necessarily have to understand the mechanism, but it helps a lot, to be able to see these kind of mechanisms and know, what each thing does. And I promise you, it'll make a world of a difference on the ACS exam. It makes a world of a difference if you start knowing what these things do. All right, and just want to make some comment. This is actually my favorite point in Orgo. This part of Orgo is just it's the most test 2 material for the most part I feel is pretty simple, but this material is where it starts getting a little bit more challenging. You have more mechanisms, you have more interactions, you have more things that occur, and there's a lot more understanding with the benzene reactions. You don't have to understand all of it. It's fairly simple, but like these are quite interesting. This is where I really began to enjoy the class, so I hope you enjoy it as well as much as I do. Um, so the first thing in this reaction, this dithiane synthesis of aldehydes and ketones, right? We have butyl lithium. So BULI is just butyl lithium, which is just CH3, CH2, CH2, CH2Li. And you know that an organolithium reagent is a stronger version of a Grignard reagent, okay? So it's basically, when you see this, you think, okay, Grignard, all right? And so what we have from before, right? Um, okay, so what we've known from before, you know that the Grignard is a strong base, right? It's a strong nucleophile, strong base, right? It's essentially a carbon with a negative charge on it. And obviously, you know that N minus is a strong base. O minus can be a strong-ish base, right? OH is a strong base. Obviously, as I go down and to things that are less electronegative, those things are even stronger bases. They're not as good as holding negative charges. So a carbon with negative charge is a very strong base. That's why a Grignard reagent is a very strong nucleophile, strong base. They're very similar terms. And the same thing with organolithium reagents. And this one in particular is butyl lithium. And butyl lithium is a bulky strong base. Okay, so what it does is it acts more as a base in this case rather than a nucleophile, and that's largely because it's bulky. So bulky things are not good. When we talk about nucleophile, we're talking about something that attacks and attaches to some molecule. We talk about a base, we talk about the abstraction of protons. So if I have something that's bulky, it's not going to really act as a nucleophile because it can't fit in because of the steric hindrance, and that's very much the case for butyl lithium. And if you tie in the concepts, what I'm talking about right here, you'll know from whenever you do exams, whenever we're trying to make a double bond, we always use Tb-toxide, right? O minus K plus. You do that all the time in synthesis, and if you don't know why you're doing that, the reason is because the bulky base will always give the double bond product. Always. It will never do SN2. It will never give us a mixed product of SN2. So it's the same concept here. I'm using this butyl lithium, okay, but it is very strong. And so what the butyl lithium does is it abstracts proton. Okay, and when it abstracts that proton, all right. Okay, and when it abstracts that proton, this is what we get. Okay, so I'm just going to get this, and let's put my negative charge. Okay, so now I have a negative charge on this, dithiene, right? And this is when we introduce the second step. Okay, so this has been step 1. Okay, this is step 2. All right, and so after step 2, what happens is we have um any alkyl halide, okay, but it has to be a primary alkyl halide. So either it's a methyl group or it's a primary, just as long essentially is the point is that it can't be bulky. So we can't have secondary, we can't have tertiary. We have to have primary or 0 degree, which is essentially a methyl. So let's say I have in the presence here I have CH3 Br. Okay, I have CH3 Br. And what happens is this is now going to act as a nucleophile, and this is going to come and kick this off. So this is going to come here and attack the CH3, and the bromine will leave. And then what we'll get, we will get this. Okay, so now I have this. And now you're asking, okay, so that's great. So this is what's shown here, right? So I've gotten this now. And now all that's left is this H3O plus and HgCl2 step. And this is where the mechanism really goes crazy. And obviously, okay, this is the addition of one R group, right? So this eventually will give me an aldehyde because I still have this hydrogen here. And then what's left, if I want to make it 2 R groups and I make a ketone, I just basically repeat this first 2 steps again. So I do this, then I do RX, and then after that I do another butyllithium and takes off the other hydrogen, gives another negative charge, and then I introduce another primary alkyl halide or a methyl halide. And then then you do your H3O plus HgCl2 step. Okay? So now this is the fun part that I like. So what happens is the first thing that they introduce HgCl2. And I'm going to try my best to, while having this mouse to do this as cleanly as possible. Okay. So HgCl2 acts as a Lewis acid. This acts as the Lewis base, electron acceptor, electron donor, and you form this. Not important for you to know. You don't have to know this, but it acts as a Lewis acid base adduct, and you get this interaction between Lewis acid and what is a Lewis base. Okay, and so after that, I get this. All right, so I've pasted this again, and now I have this interaction with the Hg, the mercury, and I have the Cl here, and now my sulfur is positively charged. Okay, so now what happens is the other sulfur, okay, is now going to contribute, and because the sulfur is a electronegative atom, right, it wants to have electrons, right? It does not want to be positively charged. It takes on electrons. It does not want to be positively charged. Just like oxygen, whenever oxygen becomes positive, it becomes a very good leaving group. And so the same thing applies to sulfur. It's positive now, and it becomes a good leaving group. And so now this other sulfur, it allows this sulfur to leave. It helps it leave by contributing a pair of electrons to form another sigma bond with this carbon, so that this carbon remains octet, and we have that stabilization. But it allows this bond to be taken away from the sulfur because the sulfur is already pulling on this bond. So this whole process allows the sulfur group to detach and no longer be positive anymore. Okay, so now let me draw another one. Okay, so now we get this. All right. And so let's just fill in the thing. So now, obviously, the sulfur lost one of its lone pairs, and so now this becomes positive, right? And this sulfur now has left with its Hg, with its mercury, that has a chlorine on it. Okay, can't draw. Anyways, you know what that is. And so now what happens? What happens at this step? So what happens at this step is now the sulfur is positive, and we have the same situation as before. We have a sulfur that's positive, but what's different is now that I have a electron accepting structure. Okay, I have basically formed a carbonyl-like structure here. So I have this double bond, and I have the sulfur, and so this sulfur is going to be pulling, up through the sigma bonds, and through the pi bond, and this carbon is going to be partially positive. Okay, so partially positive, and so this makes this carbon a electron accepting site, or electrophilic. Okay, and so what happens is, since we're doing this under aqueous conditions, right? I have H2O, I have H2O plus is going to go in these various forms. Okay, just to demonstrate. If you ask, oh, it says H2O plus, but why are you using H2O? Well, we can use H2O. It goes into these various forms of, not protonated, neutral, and positive. And so these are there in concentration a lot. I don't think as much as this. So we go in between these forms. So H2O is present, just that, because the equilibrium, I don't think the difference of equilibrium is significant. So you always get a mix of H2O and H2O plus if you're doing things in aqueous conditions. Some of it is protonated, some of it is not. Anyways, not important. So the H2O is present, and it'll act as a nucleophile. And so this structure is electrophilic enough that the H2O can come and attack it. And so the H2O comes and attacks, and then one of these bonds goes back onto the sulfur. Okay. And now let's okay, so now this is what we're left with, and let's fill in some things. So I'm gonna fill in everything so everyone can see. All right, and so now I have this guy. All right, so I have OH2 plus, right? It has a positive charge. Oh, the oxygen lost one of its lone pairs to form a bond, so now it's going to take on a positive charge. And then after this step, right, what are we doing? Okay, let's make this a little bit smaller. Okay, so obviously after this step, I'm going to put minus H over here to show that this gets, deprotonated, and then I get an OH. All right, so now what happens after this? What happens after this? Well, after this step, what happens is the sulfur over here, right, now has its lone pairs back. It's going to interact with the mercury. Okay, and so the same thing will occur. And so this will leave, and now I'll be able to form this structure. Okay, so actually I left something off. Over here, there should be a carbon group that we've added, right? That's CH3 group. And there should also be a CH3 group right here. Okay, so we have all these groups here. And now what we have, right, so we have this structure, right, so the sulfur came and attached, right, to this mercury. And so now this sulfur is positive. Okay, this is an OH. Well, actually, I won't make that the OH. I'll make this the OH. Okay, and then this is a hydrogen, and then here's our CH3 group. Okay, so what happens is now the sulfur is positive, okay, and now the OH contributes one of its lone pairs to form a double bond and allowing this bond to break and the sulfur to leave. Okay, so what I get now is this. Okay, so this is what I get. All right, so this is what I form, right? So this OH, and now let's fill in some things. So this oxygen is now positive. This sulfur is now fully, it's happy, it's bonded to this mercury. And so this is what we form. And we also form this, and this is very close to what we want in the end, right? So now you see how we've gone full circle. So now all that's left is deprotonation, and we get what we want. Okay, so this is the mechanism. This whole thing is the mechanism, and I wouldn't say that you have to fully know it, but it's very nice to see how this, especially these steps, right here, this step, and these steps right here. These are very important steps, I feel, that they will help you later on, the starred ones. And of course, step 1 and 2 are absolutely, non-negotiable. Non-negotiable. Okay? The formation of these things is non-negotiable. You have to know how this works. The function of butyllithium is, and the function of RX, obviously. Okay, so this is the mechanism. And if you want to get the ketone, so I formed the aldehyde. Ketone is just that the only difference is I repeat these first 2 steps, I do it twice. Okay, and what follows is completely the same. The H has no function in this mechanism. It's there, and it gives us the aldehyde in the end. All right, so very fun reaction, very fun mechanism to see. All right, so the next one that we have after this is this one. Okay, so ketones from carboxylic acids, and the mechanism is the use of any any organolithium reagent. So some RLi, and we do that twice, right? It's 2EQ, it has 2 equilibriums, and then we have all that followed by H3O+. Okay, so let's take a look at what this looks like. Okay, so this is kind of what we have, all right? So what happens is you have an organolithium reagent. It's a very strong nucleophile, very strong base. And so what it does is, the first thing that it does is it deprotonates the carboxylic acid, okay? The carboxylic acid, the acidic hydrogen there is extremely acidic. And so that's the first thing that's going to be removed, okay? And then once it's removed, okay, so here's what we get. We get this, okay? And all right, so now this one that we used is no longer useful, right? This carbon with its negative charge, right? It used up its negative charge to extract the proton. So now this is just a CH3, CH3. It's just a an ethane, right? Nothing special about it anymore. And so all that's left is an O minus, and we have the Li plus. So now we have this salt, right? We have this lithium salt. Okay, so O minus Li plus. Sorry, my handwriting is garbage. And then, we repeat this step again. Okay, so, alright, so there. So we repeat it again, and now I have this salt, and now all that's left is the carbonyl. So this is going to come, not very pretty, this is going to come and attack the carbonyl. Okay, and so what I get again, okay, so what I get, sorry, every time I draw it and I pause the video, and here, so this is the first salt, and this is the second salt. Okay, can't draw L's, it's very hard. All right, minus Li plus, plus, minus, and so here's the group that was added, here's the new salt that is formed. Okay, so now that I have my salt, now I move on to my next step. So this is all step 1. Now I'm going on to step 2, and this is where I introduce my H3O plus. So H3O plus is going to protonate what I have. Okay, so I'm just going to copy and paste this again. All right, and so now I just get these alcohols. Okay, and here is what you need to know. Whenever you have a carbon that has 2 alcohols on it, what happens is one of them is water is removed, right? So you move an oxygen and 2 hydrogen, which is water, and you're left with a single oxygen, and that becomes the carbonyl. And I've never actually seen the mechanism myself before, but what I'm pretty sure that what occurs when you have these 2 alcohol groups on the same carbon, one of them is going to remove the hydrogen from the other group, okay, and then this one is going to form a carbonyl, and this gets kicked off, right? Because now I've formed water, which is a good leaving group. So one of them becomes a good leaving group, the other one helps it to leave, and so eventually you're left with a carbonyl structure. And so in the end, you get a carbonyl, and I get my addition. Okay, so if anyone is confused about that last step, all you need to know the takeaway is that if you have a carbon that has two alcohol groups on it, on a single carbon, this will be reduced into just a single carbonyl, right? And don't think, I'm not talking about reduction oxidation, I'm just saying like it will be reduced. So two alcohol groups will become one carbonyl group. That's how it always occurs. And so what you're left with is now, the ketone that we've made. Okay? And so my R1 group is this group that I've chosen to add, or it was the butyllithium. I mean the the organolithium reagent that we used. Okay? So not too bad. It's a pretty nice reaction. All right, so moving on. The next reaction is the ketones from nitriles reaction. So we have a nitrile, which is a cyano group. So CN, cetryl bond N, and we're going to react this with a Grignard reagent, and then followed by a H3O plus step, which will give us the ketone. All right, so basically we're forming a ketone from any nitrile. And the mechanism for this is pretty cool. It's very similar to the other one. So the cool thing about these things is that you figure out one mechanism, you'll be able to figure out a lot of them. So let's start looking at the mechanism. All right, so let's say we have this nitrile, and let's say I have this Grignard. So I'm gonna put my MGBR right here. Okay, and so the first part of this reaction, okay, is the Grignard will come and attack this carbon right here. All right, and so this carbon, maybe I should draw this out with the actual carbon. Never mind, I couldn't get it to work. Anyways, so this is going to come and attack this carbon right here. All right, and this structure, as you've seen with other reactions and other things we've done, whether it be classifying withdrawing groups or looking at the Diels-Alder reaction, we've seen the nitrile function as a withdrawing group, and just like all withdrawing groups, they have an electron accepting structure, right? So the electron accepting structure is this carbon and this nitrogen, and this triple bond is electron. This whole setup, this triple bond between the carbon and nitrogen is electron accepting, because the nitrogen can take on the negative charge of the lone pair. So a carbon can be attacked, and one of these bonds can be pushed out onto the nitrogen. Okay, and this is electron accepting, and it allows us, withdrawing group like function. Okay, and once we get that, we have this attachment that forms. So this is what we get. This is the first step of the reaction. So these two carbons are right here. So this is 1, 2. It came and attacked this carbon, which had another carbon on it, and the nitrogen. So nitrogen now actually has 2 lone pair, and it's negative. Okay, and then what proceeds after this is the protonation. So this gets protonated, and so I have this H3O plus. Whoops, that is the opposite. Right. So I have this H3O plus, and I'm all over the place today. There we go. All right. So we have this acid, and so this is going to abstract one of these protons. All right, one of these acidic protons, and it's going to stabilize itself. And so I will get this now, which is the same, except now there is a hydrogen here. Okay, so now the nitrogen is neutral. So what, you may ask, what follows after this step? Well, what follows, right? So my goal is to essentially, what's the difference between this structure and this structure? The difference is that everything is the same, right? Imagine if this was, our 2 carbons, okay? Imagine if that was our 2 carbons, all right? The difference between this structure and this one is the nitrogen. So I have an oxygen double bond, I have nitrogen double bond. I need to get rid of the nitrogen and replace it with an oxygen. So that should make me think that I need to introduce H2O to come and attack at some point, right? I need H2O to come in so I can introduce an oxygen bond to my molecule, and specifically this carbon. So how do we go about that? The way we go about that is the next step is going to be, again, another protonation step. So this nitrogen is still basic enough that it is more basic than than this H3O plus here. So this is acidic enough that this can get protonated, right? So this will protonate this. Okay, H3O plus is fairly acidic. It's a fairly acidic molecule. It's an oxygen with a positive charge, and it's pretty acidic. So this nitrogen will get protonated again, and okay. So I need to, right, there we go. Here. So what happens is this nitrogen will now have another hydrogen bond. And now it will be, well, actually no lone pairs, right? 1 second. Yes. So yeah, no lone pairs, right? Because we came from 1. And so now we won't have any. And now the nitrogen will have a positive charge. And now that the nitrogen has a positive charge, this structure is going to have a dipole moment. It's going to have a much bigger dipole moment than it did before. So this carbon right here is going to be very partially positive, right? So basically I've activated this structure by making this nitrogen positive. I've now made this carbon over here much more electrophilic. And so now H2O, which is a weak nucleophile and a weak base, is now strong enough to come and attack. Okay, so now this can come and attack. And now this will push this up to the nitrogen. Exactly what I want. The nitrogen wants those electrons. Okay, so I've put everything here that that occurs. So once I accidentally had the video paused. I'm not sure where I left it. The crappy move. But so bear with me here. So we start. This gets protonated, and this becomes a good leaving group. So the NH3 now forms. It's pulling on the carbon sigma bond and making this carbon right here partially positive, right? And this is becoming a good leaving group. So at this point, the oxygen contributes one of its lone pairs to form a double bond, and this is allowed to leave. And so once it leaves, now all we get is the oxygen carbonyl structure with a hydrogen on it, and it's positive. And then all that remains is the deprotonation via H2O. H2O will come and deprotonate this, and we'll get our carbonyl, right? And this is our ketone that we want. And so this is how the mechanism progresses, and it's fairly simple, I believe. And it's a bit roundabout, but if you understand the process of how we go from one thing to the next, it will help you a lot. All right, so not too bad. All right, so the next reactions are the use of acid chlorides, and one of them is formation of aldehyde, other one's formation of a ketone. And this is from acid chloride. So there's specific functional groups that we're using, and we're converting them into either a ketone or an aldehyde. So aldehydes from acid chlorides, you use either LiAlH, OTBU3, right? Lithium aluminum tri-T-butoxyhydride. And then you can also use Rosenmund reduction, which is H2PD BaSO4, and I'm not sure what the S is, but I guess S. But anyways, you don't really need to know the mechanism for these. I don't really know them myself. And you just need to know that it goes from acid chloride to aldehyde. So this is ones you have to memorize. And then this one as well. And the way I usually remember this, we actually have seen the formation. It says here, make sure you know how to form the Gilman reagent. And we actually have made this before, shown it before in the Orgo 1 reaction sheet. It says refer to the Corey-House reaction. But I don't really think you need to know how to make it. It's not important. It's not like a mechanism that you understand or something like that. It's another thing you memorize. But you go from an acid chloride and use any carbon, and it has 2 of them on the CuLi. So basically, like for example, if it was like CH3 2 CuLi, the CH3 would be the group that is added here. Okay, so that's all you need to know for these, and this is just simple memorization for these ones. And now we're on to our last reagent for today, And this is going to be the fun one. So the last one that I'm going to show you guys for today is the Wittig reaction. And essentially, so there's two things I'm going to show you. I'm going to show you, how to form the phosphorus halide, and I'm going to show you the reaction itself. And so the Wittig reaction, essentially, it will replace a carbonyl, right? Any carbonyl, so aldehydes or ketones, not any, but like the main ones, ketone or aldehyde, and it'll replace it with a double bond, essentially. And you'll get a mix of products, but obviously the one that is the least sterically hindered is your major product, right? This is the cis product, and this is the trans product with the big groups and trans. This is the major product because it's the most stable and it's the most, you know, least steric hindrance between these two substituents on the double bond. All right, so this was too hellish to actually just make on my own, so I just drew it out. So I just want to demonstrate the reaction. So first things first, this is the reaction over here. This is the preparation of the reagent. So I'm just going to talk through it and just show you guys what is going on. So first thing we have is we have this, the Wittig reagent right here, right? So I have the pH just means you have a benzene ring. So pH 3 means 3 benzene rings. So 3 benzene rings, all right, and it has a positive charge, and you have a carbon with a negative charge on it. Okay, I didn't draw the negative charge, but here there is a negative charge. Okay, and in the first step, what happens is this attacks a carbonyl structure. So either an aldehyde or a ketone. This is the one that they've chosen to demonstrate the reaction. This is the aldehyde that they've given you for the reaction example. So this attacks the carbonyl, aldehyde, or ketone, and you form the structure. Okay, so you form this carbon, which has its hydrogen and the R group, and has this bond to the phosphorus, and has the 3 benzene rings on it. And then after this, what happens is we also get an oxygen with a negative charge, and the oxygen and the phosphorus, they form, a Lewis acid base, interaction here. Oxygen negative charge, you have electron acceptor over here with the phosphorus, and so you form this interaction here. And so once this forms, you get this molecule, and what happens is the molecule collapses. So the oxygen takes this bond and it forms a double bond with the phosphorus, and then with the phosphorus it loses this bond with the carbon, and this is used to form the double bond. So what happens is this top part goes away, and then you're left with the bottom part, which forms a double bond in between the 2 carbons. The double bond between the 2 carbons, and then this is what forms your product, your double bond product, your alkene. And so you can get both a cis and you can get a trans product, and obviously the major product is going to be the one that is the most stable one. And so the takeaway is basically what happens is you are simply, okay, so I'm just going to demonstrate, you're cutting here. I'm going to demonstrate the easiest way, the dumb way to go around about this reaction. You're cutting, this half of the reagent, whatever, all right, and then you're also cutting this half of the reagent, and so all we're doing is we put it together. Obviously this should be a little bit bigger, whatever, and here's our double bond. And that's what you're doing. This is a very simple way to get it right every single time. This is what you do. So you take this half and you take this half and you put it together, and this is the answer. So I've gotten the major product. This is the major product. The other one is just with them on the same side. The only other thing that's important to demonstrate is the preparation of the phosphorus halide. So this is the phosphorus forming the phosphorus halide, which is what we're using over here. Okay, which is which should be this one, I believe. Yes. So this one just is just demonstrating with the double bond. The only difference between this one and what I have over here is that I have it split up into the positive charge and the negative charge. This is the double bond where where it's neutral. So how do we form this? The way we form it is that we have a phosphorus with whatever 3R groups on it, and we introduce it to a primary alkyl halide or some electron acceptor, and we get this attachment. So it comes and attacks, and then leaving group leaves, and then I get my my phosphorus with a positive charge, and I get my CH3 group. And then the second step, I use butyl lithium, and butyl lithium will deprotonate the CH3 group or whatever carbon group that has some hydrogen on it. It has to have a hydrogen on it, right? You have to have at least one hydrogen for this to work. And so this gets deprotonated, and I get my useful reagent. So this is what I use, to perform my reaction. So I use this in the combination of any ketone or aldehyde, and I will perform the Wittig reaction as a result. And this is all you guys need to know. So I hope this video helps, and I really hope that you are able to use the video to get ahead and now properly do all the reactions. Study hard and just make sure you really put in the effort for this exam, because the third exam is going to be difficult. So it's very important that you don't lose this opportunity to do your best and study as much as you can for this coming exam. All right, best of luck.